Climate engineering. Trenching. Forest destruction compacts vast tracts of the world's land surface, rendering it impenetrable to rainwater infiltration. Trenches excavated along selected contours restore the soil's infiltration capacity by renovating underground water storage. Year-round accessible subsurface volumes ensure the re-emergence of grasses, shrubs and trees. Trenches can be excavated by hand or machine, making it affordable for all walks of life above poverty level. Its land use furnishes sufficient manual labour, whereas sparsely populated regions are easily treated with earth-moving equipment. Drains infiltrate the rehabilitated land and saturate underground, revealing biodiversity, however dormant. The initiated evergreen cycle of the treated earth has thereby started in earnest. The same rainfall in torrential discharge rips non-contour trenched land apart, through erosion followed by landslides. On the other hand, a more pacified and evenly distributed rainfall has the same devastating effect. These opposite rainfall patterns bring death and destruction on non-contour trenched land. Both patterns have an uninterrupted, life-generating impact on contour trenched earth. So what makes water, which is the condition for life, so lethal outside these treated boundaries? Creating water for human consumption. Water is fundamentally lazy and always in search of the easiest and fastest flow in order to go and lie dormant. It will flow to the surface at the last trench and proceed as surface water to the easiest accessible lower destination. Before it reaches the surface, the water flow can be transferred as consumable water in a piped conduit. The more this contour trench system is expanded in altitude, the greater the pressure of drought-resistant, year-round water which can be achieved. Creating year-round water for animals and plants. Wasteland with 100 millimeters of annual rainfall receives 100 million liters of water per square kilometer per year. That water volume is sufficient to turn desert land into forested grassland and to provide 20 liters of water per day to 1,600 head of cattle and 300 liters of consumable water to 440 people every day of the year. Excess water pushed onto the land surface can be recycled into an evaporation-free underground flow. A horizontal stone wall construction disperses the concentric surface flow towards the next contour trench formation. In this way, accumulative surface water sources can be established wherever and whenever desired. 200 square kilometers of forested grassland increases local rainfall by 20%. River water dispersal into subsurface infiltration. When surface runoff water drills deeper into the land, the time has come to divert that water into a productive flow pattern. These seasonal rivers have the tendency to sink even deeper, thereby draining both runoff rainwater and groundwater. The land starts to leak to the point of finally drying out, except for some deep-rooted trees and superficial seasonal vegetation. A low dispersal wall at the beginning of the riverbed diverts shallow, silt-poor river flows into the contour trench unit. Downstream, a higher wall in the eroded riverbed centralizes torrential, mud-filled river water back into its original stream pattern. Walls at the higher side of the contour trenches filter and distribute the diverted river water into an overland sheet flow. The waters then infiltrate into the soils to become an underground and cool, clean flow into the dam. In the course of the rain season, the rejuvenated vegetation cover turns into the natural filter and distributor of future river water. The current turns into evaporation-free storage and coolant of the dam's surface water once the rains have ceased. As a result, the dam becomes a year-round surface water point if consumption does not exceed subsurface infiltration. Turning Kilimanjaro's glaciers. Destruction in the Kilimanjaro region left Africa's highest mountain as a lone and incontinent giant. Twice a year, heavy rainstorms from the Indian Ocean enter the mountain's hemisphere. These saturated rain clouds torrentially discharge when forced towards higher and therefore cooler altitudes by the mountain elevation. Unable to accommodate this instant local water increase, these volumes quickly and therefore destructively discharge towards surrounding land depressions. Once settled there, they evaporate during the dry season in the heat of the scorching sun. These cloud formations disappear beyond the horizon, enhancing further flood risk in the west. A doubling of the Kilimanjaro forest through the construction of water dispersal and infiltration units preempts rainstorms through more evenly distributed rainfall. They achieve this through extended forest humidification and subsequent cooling. The remaining lighter rain clouds are propelled by wind elevation towards the summit. A further growth of the glacier is generated by increased forest evaporation, responsible for rainfall extension into the dry season. Urban water, food and energy production in Bamako, Mali. Why would one continue to pump, filter, and chemically treat polluted river water to make consumable water? River water which above all originates in a foreign country beyond national control, and which is increasingly subjected to climatic extremes, varying between El Niño floods and La Niña drought spells. When consumable water for urban inhabitants can be produced, why would one continue to pump, filter, and chemically treat polluted river water when consumable water for urban inhabitants can be produced to double, triple, or in the case of maize as an improved grass species, quadruple agricultural yield? And where that very same consumable water volume can generate the energy to electrify and mobilize beyond the capital's demand. Where beef and dairy cattle can be used for land management guarded by inedible, energy-generating jatropha hedges, showing the optimum grazing pattern towards evergreen grass and weeds, sprouting from always humid soil conditions. Climate coolant. Bamako's agricultural runoff area receives an average 120 million cubic meters of water from one rainy season per year. If this volume were to be stored subsurface at a cost of some 27 million euros, 300 square kilometers would turn evergreen. Temperatures would decrease by an average 20 degrees centigrade, while precipitation would increase during the dry season by some 20 million cubic meters. This 140 million cubic meter consumable water volume can be retailed at a very affordable price to the community. Cooling pays and will continue to do so, permitting human resourcefulness and ingenuity to take the upper hand. Wind-propelled, water-processed fertilization. Dust storms are the final, potentially fertile terrestrial cooling systems in our biosphere. When they're left unattended, the dust will finally blow away, making way for high-speed sandstorms. The resulting dune deposit ultimately strangles the last remaining vegetation in seasonal extending territory. Dust, however, is a fertilizer, embedding dormant biodiversity within evergreen sand plains. When sand-reflected atmospheric heat finally attracts cooling rainfall, the time has come for a seemingly magical amalgamation. Dormant dust, deposited in the contour trenches and flooded with rainwater, turns into the forest of the future. Fertilizing dust was deposited by wind, and commercial seeds are distributed by runoff water. We can leave the forest as it is, or decide to recolonize deserts with commercial plantation. No manual plantation is required. Human labor is only needed for the removal of surplus and misplaced germination. Maritime rainstorm preemption for continental flood mitigation. Every year, when the Northern Hemisphere faces the direct heat of the sun, daily atmospheric clashes ensue from desert-reflected solar heat. In search of accommodation, these excess heat volumes turn to the relatively cool Northern Atlantic Ocean waters. These waters with a limited carrying capacity release surplus heat through evaporation back into the atmosphere. The relentless combination of the sustained entry of hot desert air triggering a daily expanding vapor flow results in giant rainstorms. Rainstorms searching for release only require a decrease of a few degrees centigrade to trigger a bombardment of rainfall. The European continent, with nearby land elevations such as the Pyrenees, Alps and the Apennines, is the obvious target. Most of these hot, thermodynamic rainstorms enter over the Iberian Peninsula, making it Europe's major hydrologic front porch. It's a gateway requiring contour-trenched, evergreen, forested grass development to preempt these storms in evenly distributed rainfall. Hurricane prevention. Should European action lead to the alleviation of the Saharan-instigated flood problem, it would mean that a symptom had been eradicated, not the cause. As the world turns, hot desert air continues to bring ocean water to the brink, where rain circulation above the Atlantic is an insufficient coolant. And when it meets with earlier overheated equatorial ocean water in search of thermal relief, an atmospheric monster is born. Hurricanes circling with the speed of Formula One racing cars rage over the Caribbean and into the southern United States. Every year, the turbulence only dissipates when sufficient water debris mixture from vast tracts of destruction cools them down. The Energy Information Administration expects a 60% upsurge in world energy consumption by 2030. Biodiesel production on land surface the size of the Sahara and Arabian Peninsula put together could cover that demand without requiring fossil, solar, wind, or nuclear energy.